Okay, welcome to video for the day one. Today we're going to talk about linear versus exponential functions. So we've already learned all about linear functions. Those are our lines, and we graph those with using y equals mx plus b form. Now we're going to also talk about exponential functions, and they're a little different. We'll talk about all the key differences in a little bit. So first, let's look at this table. We have this 0 with -5, and then 1 with 2, and 2 with 9, 3 with 16, 4 with 23. Well, for those points, I'm trying to figure out what's the pattern so I can fill in the rest of my table here that's missing. So on the left side here, it's easy. I can see that it's going up. So I can go ahead and fill in the rest of those with my 6 and 7. Now, with the y values, -5 to 2, how did I get from -5 to 2? Well, I think I added 7. And then we just need to see, did that continue? 2 plus 7 is 9. 9 plus 7 is 16. 16 plus 7 is 23. So that tells me that I can add 7 every time. This is a constant rate of change, just like what we've talked about before, as the change in y over change in x. So as I go up 7, I go up 1, and that's my slope. So now I can continue this pattern to fill in the other values. So 23 plus 7 would be 30, 30 plus 7 would be 37, and then 37 plus 7 more would be 44. Okay, now these points were a little different. So I drew in axes, but as you can see from my picture here, I switched them so that I could show more of the graph. Since 0, -5 was the smallest I needed, but I needed to get up to, close to 744, I knew that I needed to count by a bigger number on my y's, even though I could count by ones on my x's since they were only going up by 1, and my highest y value, or x value, is the 7. So I changed my scale a little bit. Now, I'm still not going to fit everything, but this will show me more of the graph. So 0 down 5 would be my first plot, which since I chose to count by 2's, it's going to be in between two of those lines there. And then the best that you can. And then 1 is up 2, and I counted by 2, so it's only going to be up 1 block, even though that's up a value of 2. And then at 2, I'm up to 9, so I have to go in between again. And then 3 is at 16. So 10, 12, 14, and 16, and then so on. I'll still see my linear function because I've adjusted the scale so that it's still counting by the same for each block. So even though these look a little different, when I connect them, I'll still have a nice straight edge and be able to make a straight line that connects these points. Now the last plot that the point that I can plot on here is 530, because after that it'll go off my grid. But now that I have those, I can connect them with a straight edge, and then I can see my linear function here. So I have a straight line. Now, what are the key components here? Well, the first thing that I noticed is that the table showed me a constant rate of change, or adding 7 each time. The second thing is that it forms a linear function. So that means I could write the equation by using y equals mx plus b form. What is the slope? What did we change by each time? Well, the slope was up 7 to the right 1. So rise over run, that would mean that my m value is 7. And the y-intercept I can also see because I know that when the x value is 0, that means that I'm on the y-axis, and I can also look at the graph, the y value would be -5. So this tells me that the rate of change and the y-intercept can go in to write the equation of the line y equals 7x, so that because that's the slope, mx, minus the 5. So that would be the equation of the line. So those are the two main things. We have this constant rate of change shown with a common difference in the table, making it a linear function. Now this next one, when I look at the table here, again I can see that my values for the x's are going up by 1, so I can fill in the rest of those. And now when I look at my y's, from 1 to 2, that would be +1, but that doesn't follow through because 2 plus 1 would be 3, not 4. So that doesn't have a common difference this time. What can I do to get from 1 to 2 to 4 to 8? Well, we can multiply by 2. So that tells me, since I'm going to multiply by 2 each time, I can fill in the remaining values by multiplying by 2. So 8 times 2 would be 16. 16 times 2 is 32. 32 times 2 is 64. 64 times 2 is 128. So again, I'm going to need to adjust my scale so that I can show these values, or as many as I can, to get an idea of what this relationship looks like. Okay, now since I didn't have any negatives, I'm going to choose to go ahead and make an L-shaped graph. Now that's not to say I can't have negatives, so I can still have an arrow on the left here, but I just think that this will be a good way to show the graph a little better. But it doesn't stop necessarily. This could keep going. I could have chosen to show some of the negative values also, but I decided to just plot the points that are here. So 0, and now I need to get all the way up to, well, close to 128. So I'm going to count by 4s on my y values, and I'm still going to leave this bottom one counting by 1s. Now, choosing that scale only gets me up to 80, so I can't plot that last point, but that's still a good representation of my graph. I can plot a lot of the points that were given to me. So now we can go ahead and plot 0 is up 1, so that's really close to the bottom here since we counted by 4. So if you can think of that one's like dividing it into fourths, so I went a little less than halfway. Then I'm going to plot my 1 is at 2, that's about halfway, since I am counting by 4s. And then the next one is 2 up 4, so over 2 up to that first line there, because remember we're counting by 4s again. And then keep plotting those points. The next one would be 3 up to 8, so that's actually 2 blocks up, again, since we're counting by 4s. And then 4 is at 16. And then 5 is at 32. And then 6 is at 64. But I can see already that this is not going to be able to be connected with a straight edge. I don't have a linear relationship here. There was something different that was shown in the table. I didn't add each time, I multiplied by 2. So that shows me that this is a different function. So now we're going to connect, again, not a straight edge this time, we're just going to connect with a smooth curve. There are a few key factors here when we talk about exponentials, and we'll get more into them as we continue graphing them. But we need to use a smooth curve, and I'm sure yours will even show a little better than mine, since the iPad doesn't always make the smoothest curves here. So we can see here the key things are to make sure that you have the arrow, you don't go up vertically, and that you show that this is continuing to go out and it's not curving up. And actually mine even shows a little bit of a curve. I'm going to erase that and show that it's just going to continue getting closer and closer over here. But it's not going to actually ever hit this y value of 0. It's going to get closer and closer and closer, but it's not going to hit it. Okay, so what are the key components? So the first thing is that the table shows a multiplying pattern of times 2 each time. This means that it'll form an exponential function. This is our new function, exponential. And we know that because we can see the common rate, the times 2 each time. That shows us that it's not going to be linear, and since it's multiplying, it's exponential. So now we could find the initial value, the A, the starting value, and the B, the rate, what's happening each time, and fill in the equation if we wanted to. So the starting value, the initial value at 0, when the time is 0, the Y, the output is 1, and then the rate, what it's multiplying by every time, is 2. So now we could fill in Y equals A, the 1 times b, and then raised to the x power. So that would be our equation that we would write to represent this exponential function. Okay, so some key things here. For linear functions, what did we find out? We found out that the table pattern shows adding or subtracting by the same number. This pattern is called common difference. The rate of change is constant between intervals. Now, exponential functions, the table pattern shows multiplying or dividing by the same number. This pattern is called a common ratio, and the rate of change is different between the intervals. It's not a constant rate of change. Now, the only thing I'm going to add up here is that I'm going to put the d by the common difference. That's what we'll use to represent the common difference. So we'll write d equals under the table, and then when we have a common ratio, we'll use the r to represent that. Okay, so we're going to continue these in class with more practice graphing the linear and exponential functions shown below. Have a great day.